Hi everyone, today we're going to be looking at entropy, which is denoted by the symbol S. It's the measure of the amount of disorder in a system, so a positive delta S would be an increase in entropy. So looking at a real-world example, if your room became messy, there would be an increase in entropy. So nature tries to increase entropy if possible. Now a negative delta S would be a decrease in entropy. So once again, looking at our real-world example, if you cleaned your room, you would have decreased the entropy. So like I said before, nature prefers to have an increase in entropy. So just to make a quick little connection here, let's look at spontaneous reactions. So it's really useful for us to be able to answer the questions, why do some reactions happen spontaneously and others don't, right? And entropy actually factors into this when we look at something called Gibbs free energy. So Gibbs free energy definitively determines whether or not a reaction is spontaneous. So a reaction with a negative delta G is always spontaneous, while a reaction with a positive delta G is never spontaneous. So the formula for this is delta G is equal to delta H minus T times delta S. So I'll just define all those variables. Delta G is Gibbs free energy. Delta H is the enthalpy, which is actually the amount of heat exchanged in a reaction. T is temperature in Kelvin, and delta S is entropy. So that's how entropy connects to spontaneous reactions. That was just a quick little connection. I don't want to go too into depth with this for this video, but if you have any questions, feel free to leave them below, and I can definitely make a future video on this if you guys want, so just let me know. Now, I want to look at some general rules for changes in delta S. So sometimes we need to know whether or not entropy is decreasing or increasing, if there's a positive delta S or a negative delta S, and these rules will help us determine that. So the first one, as a substance goes from a solid to a liquid to a gas, the change in entropy is positive. So the entropy increases. And I think we can kind of logically explain this, right? Because if you're going from a solid to a liquid to a gas, the particles are moving more and more. Like in a solid, they barely move. In a liquid, they're kind of moving around each other. And in a gas, they're whizzing around. So there's more and more movement, and this increase in movement is accompanied with an increase in disorder, right? So it kind of makes sense that our entropy is positive. And the same is true vice versa, right? If you're going from a gas to liquid to solid, these particles are kind of becoming more and more compact. So it kind of makes sense that our entropy, I said enthalpy by accident. I meant entropy. Our entropy is decreasing. So our second rule is that if a solid or liquid is dissolved, it results in an increase in entropy again. So I think once again we can logically think about this and understand this, right? Because if you're putting a solid in liquid and it gets dissolved, there's more movement and there'd be an increase in delta S. But the opposite is actually true for gases, right? Because these gases are being dissolved into this liquid, there's less movement, they're kind of being forced in. So it would make sense that the entropy would decrease if you just look at it in terms of movement and how they would be moving when they're being dissolved. So our third rule is now talking about a reaction that has no changes in physical state. So unlike the first rule where they're going from solid to liquid to gas, there's no changes in physical state. So how do we know whether or not the entropy is decreasing or increasing? Well, we can figure that out through the number of gas moles, right? So if the number of gas moles on the product side outnumber the number of gas moles on the reactant side, then there's an increase in entropy, right? And I think we can look at this and kind of understand this once again, because if you're going from, because basically what we're saying is if you go from less gas to more gas in a reaction, then these particles are beginning to move around more, right, after this reaction, so there's going to be an increase in delta S. And then the opposite is true as well, right? So if you go from more gas moles in the reactants to less gas moles in the product, that means the particles are becoming more compact, there's less particles whizzing around, so there's going to be a decrease in entropy. So hopefully that makes sense. Let me know if you have any questions on that. Oh, and if you're needing a refresher on moles, I think we have a video on moles and explaining them in general, so definitely check that out. Okay, and so the last rule I want to talk about is that an increase in temperature is almost always an increase in entropy. And I think this kind of connects to the other rules about movement, right? Because an increase in temperature, like temperature is related to the average kinetic energy of the particles, right? So if the temperature increases, the average kinetic energy of the particles increases. And if these particles have higher kinetic energy, they're moving around more, and there's going to be more chaos, more disorder, and therefore the entropy is going to be higher, right? And so the opposite applies as well if you're having a lower temperature, if you're having a decrease in temperature, right? These kinetic energy is going to be decreased, these particles are going to be moving around less, and there's going to be a decrease in entropy. So those are the general rules for change in entropy, and this is just a general overview of entropy. I hope that was quick and useful. If you have any questions, as always, feel free to leave them below or email us, and I would be so happy to help you. Thank you so much for watching, and I hope you have a great day.